92 by 112, and how many will there be? 30, for a PCA.
Yeah.
So that if we multiply these two, what will we get? I transpose times the basis matrix, 1 by 30. You guys agree?
Yeah.
So this will be the projection of an image onto the reduced basis, onto the reduced dimensions. Okay, so now I'm asking the same question. If we're using LDA, in LDA, we don't pick the number of reduced dimensions. It's decided by number of classes. Okay, we can go below that, but we cannot go above that. Okay, so number of classes minus 1 is the reduced dimensionality in LDA. Okay, so my question now to you is, what will be the size of this matrix over here that eventually, as we apply the LDA algorithm, will need, so what will be the size of that? 39, because we have 40 classes, 40 minus 1, 39, so this will be 39. Okay. Then any number that we get, we'll project it onto these 39 dimensions and we'll get 39 numbers. Okay. So how will the face recognition work in LDA? Okay, for the known 200 images, so same way, we'll pick the training data set. Each one will be represented by 1 by 39. Do you guys agree? So this is how we'll prepare the data set. Okay. Now suppose somebody gives us an unknown image, IX. How will we know which one is it? We'll do IX transpose times our basis matrix. Okay, so what will it give us? Won't it give us 39 numbers?
Yeah.
Then what do we do?
We compare those.
Do a Euclidean or a correlation with all of those, and whichever produces the closest, whatever that label is, that's the person we are recognizing as. Okay. So let me briefly go over the LDA part. So this week, if you can at least get this to work, and then start an LDA. Like I said, it's a very small modification to whatever we have over here.
Sure.
Okay, majority of the infrastructure stays the same. So let's go and okay, so then as I showed you in your next assignment, you will redo the same thing and then see how's the accuracy with LDA. The expectation is it will be a little bit better because it's trying to do a better class separation between the data, right? So let me briefly take you to the same handout we were following, and now, okay, so obviously you will go through and let me go refresh your memory on the main algorithm. Okay. Okay, we already talked about, why the variance also needs to be taken into consideration when deciding what should be the projection vectors. Okay, because if we simply look for a projection vector for a two class problem, there will be a single 2 minus 1 is 1. Then it will pick this to be the projection, but some of the red data, blue data will not be distinguished properly. The proper should be not only we consider the mean, but also the variance to decide what should be the projection vector, right? Okay, so anyway, the math behind it is not too bad. I'll just So the first part of this was previously when we were creating the covariance matrix, right? It was, remember, I transpose times I. But when we assembled I, did we care what class the data belongs to in a PCA? No, right? So here, how many classes do we have? 39. So how many means will there be? Each class will have its own mean. So there will be 39 means, right? So there will be 39 covariance matrices. Sorry, 40 classes, my mistake. Because up to this point, we are still, every class has its own mean. Okay, so the 5 images that you have in your training data, you'll basically compute a covariance matrix only on those 5 images. And then, so basically this is the covariance matrix, as you can see, for class 1, class 2, and so on, right? And so then basically, like I said, this will go up to 40. And so then we call this matrix SW. Okay, once we have the SW matrix, okay, so then we also create what is called an SB matrix between class. So let me, where was the definition? Yeah, here's the definition of SB. So if you take a look at the definition of SB, okay, so this is basically between each pair of means, like, so in our case, what will be the mean of each class? What will be the size of it? So mu1 or mu40, what will be the size of each one of these?
The same size of the photo, the 92, about 102.
90 times 112 times 1, right? Okay. So if we did, for example, this times this transpose, so you will see will produce a huge matrix. Okay. But this is for a 2-class problem. Okay. So what the author does is author shows us a 2-class example first, then generalizes it to as many classes as we feel like it. Okay. So, okay. Hope you guys can go through this later on, this example, and see if it works, but let me just go to the N-class problem. Where is the N-class? Okay, so C classes, right? Okay, so if you take a look over here, let me go to, let me go to this part here. Okay, so first let me explain the author's terminology over here. Okay, so this y is basically our projection. So if you take a look over here, we are now seeking C minus 1 projections, y1, y2, C but means some projection vector W of I, right? So, so this size will be basically 1 by 39 in our example, right? Okay, this W over here is our, the basis, or the basis matrix. Okay, so each one over here will be basically 92 times 112. Right? And how many will there be? 39 of these. Right? Okay. So there's two ways of doing this. For example, if we do, so this will be 92 times 112 times 39, correct?
Yeah.
Okay, so if I did a transpose of this, as you can see, this will become 39 times. Okay, then if I move X is our, like, one of the images, which will be, again, 92 times 112. Okay, so in their terminology, rather than getting the projection as a 1 by 39, they are getting the projection as 39 by 1. Okay, but it doesn't matter, still we have 39 numbers in the end, right? So that's the goal. And okay, so basically there are two matrices involved over here. In LDA, two main matrices. Okay, one is the, what did they call it? SW, I think was that called, within class, and one is called SB. Okay, this one is easy, right? This was S1 plus S2 plus
However many classes.
however many classes. This is the covariance matrix for each class. Okay, this one over here, let me see if I can show you for multiple classes, what will it look like? Yeah, somewhere over here. Okay. So SB is basically this formula over here. I equal to 1 to C's. What's C in our case?
Classes? 40?
40. N of I is basically the number of images belonging to each class. Okay,
5?
so which is 5. And then mu I minus mu. So mu I we already know is the mean of that particular class. Can you guess what mu is?
The total?
Is the total mean. See if you take a look over here, n in our case will be 200. X is basically each image. So this is really the mean of all. So basically SB will be computed as mean of that minus the mean of the so once we have the SB matrix and the SW matrix, those, so like I said, this was easy. Okay, let me quickly show you where they have SW somewhere over here as well, so that, yeah, so see over here. So take a look at SW, right? Isn't this S1 plus S2 plus S40 goes up to C, correct?
Correct.
So basically, can we compute SW? Yes, right? Because this is basically each covariance added. Okay. Can we create SB? Once we looked at that formula, it's basically mu I minus mu for each class in the transpose, right? So these two can be calculated. Once we know these two, so once we know as within class, between classes, then last part is what do we do with it? Okay, so let me show you. Okay, so then basically, what we do is SW inverse. So what we compute SW, S1 plus S2 plus S40. We compute SB, whatever that mu I minus mu, and then the transpose, and whatever that formula that you guys saw, right? So once we have these two, then you compute SW inverse times SB. Okay, compute the eigenvalues. Okay, and then the, so in our case, let's take a look over here. What will be the size of SB? Okay, so remember this was
92,
It's from I to C.
By 92,
So there's 40, right?
no, those were being added, but after we add all the matrices, what will be the size of SW? This will be 92 times, because if you recall, this was basically x minus mu of I and x minus mu of I transpose, right?
Yeah.
Okay, so x is 92 times 112. Mean is also 92 by 112. So if we do transpose, so won't it be this times 92 by 112?
Can't spell.
No, that's it, yeah.
Can't do that.
No, it's a transpose. So this is 92 by
So they're 92
112
by 92?
by 1, right? Then if I did the transpose, wouldn't that be 1 times? So the final matrix, SW, won't it be 92 times 112, whatever that number is, times 92 times 112? Right? Okay, so same way, if we take a look at SB, SB will be mu I minus mu. So this will also be, okay, this also will be 92 times 112 times the 1 times 1 times 92 times 112. Right? So SB size will come out to be what? Same, right? Meaning this size. So if we compute the eigenvalues, eigenvectors of it, how many will there be?
92 times
112 eigenvalues. If we sort them by magnitude, right? And keep how many top?
39.
Top 39, that will be our projection. So you can see easily we'll get
39 by 1.
39 by whatever, 92 times 112, right? And then any incoming image, we just project it onto this and we get 39 numbers. Piece of cake. You'll have it ready by tomorrow. So anyway, give it a try, and if you can't do it in a few days, I'll give you my solution. But like I said, this has very important implications. If you are able to make it to today's deep learning class, there's one part which still is common between us and them, which I'll be covering today, which are basically variational autoencoders and autoencoders. And so the insight you'll develop in that, this will help a lot. Why are we doing that? Okay. So anyway, I'll stop here.